This opening cell sets the context for why portfolio optimization is useful. Here we import the libraries we Eurostrade LL need, define the DAO tickers, download price data, and clean missing rows. Here's the narration for this Jupyter notebook. Welcome back to our optimization walkthrough. In this cell, we're going to calculate the daily returns and annualized statistics of our portfolio. We'll use these stats to inform our optimization model. First, let's import any necessary libraries, in this case, just NumPy for some math operations. Now, we'll compute the daily returns using Pandas PCT change function, dropping any missing values along the way. Next, we'll annualize the mean and covariance of those returns by multiplying them by 252, which is the number of trading days in a year. This gives us our expected returns and covariance matrix, respectively. We'll also extract the tickers from our data and store them in the n variable for later use. Now that we have our daily returns, let's define the current portfolio weights. This will be used as an initial condition for our optimization model. In this case, we're assuming a uniform distribution across all assets, but you can also start with a cash allocation if you prefer. Moving on to the optimization itself, we'll define some key parameters. Gamma, which controls our risk aversion, cost rate, which is the transaction cost per unit of turnover, and turnover limit, which caps how much of the portfolio we're allowed to trade each period. We'll then define our decision variable, in this case, the new portfolio weights. We'll also define a constraint that ensures all weights sum to 1, so we're fully invested, and another one that keeps us long only. Finally, we'll set up an objective function that maximizes the mean variance return minus linear transaction costs. We'll use the ecos solver from CVXBY to solve this optimization problem. And finally, we'll print out some diagnostics on the status of our solution and its optimal value. This is a critical cell because it represents the core optimization model we're using to make portfolio decisions. The output here will inform our investment strategy going forward. So let's see what happens. Now that we have our optimized portfolio weights, let's get a summary of the portfolio's key metrics. Here, we're pulling in those optimized weights and creating a Pandas series from them. We then sort these weights in descending order and take the top 15 ticker symbols to see what our most heavily weighted assets are. Next up, we're calculating some important statistics about this portfolio: turnover, costs, and other key metrics. We start by finding the realized turnover, which is essentially how much of the portfolio has changed since last time. This can help us understand the impact of rebalancing on the portfolio's value. We then calculate the expected return on this portfolio based on its current weights and the historical returns of each asset. Alongside that, we're calculating the portfolio's volatility as well as a Sharpe ratio without considering any risk-free rate. This gives us an idea of how much return we can expect from the portfolio relative to its level of risk. Finally, we calculate the estimated transaction cost based on our turnover and the cost rate for each trade. Let's go over this code step by step. We're looking at a function called optimize portfolio, which is a key component of our portfolio optimization algorithm. This function takes in several parameters: the expected returns mu, the covariance matrix sigma of our assets, and some other hyperparameters like gamma and cost rate. Now, this function is where the magic happens. It uses a clever linear programming approach to find an optimal weight allocation for our portfolio based on maximizing returns while minimizing risk. The code starts by converting the input arrays into NumPy arrays, which are then used to define the variables and constraints of our optimization problem. We're using a technique called quad form to compute the quadratic term in our objective function. We have three main goals here: maximize the expected return of our portfolio, minimize the risk measured by the variance, and also try to avoid excessive trading by keeping turnover below a certain limit. The function returns the optimal weights wopt, along with some information about the status of the optimization process. Now, let's execute this code. We're passing in the expected returns mu and covariance matrix sigma, as well as some pre-computed weights wprev. The rest of the hyperparameters are set to their default values. The result is a series of optimal weights for each asset in our portfolio. Let me run this code. So here we have a Jupyter notebook cell where the code is trying to concentrate the investment distribution by taking only the top 10 securities with the highest weight. This is done to eliminate the messiness in the original top 30, where some securities have less than 1% allocation. Let's start by importing the necessary libraries. Quickly scrolls through the imports. Okay, we're good. Now let's look at Finicode. weight equal to value up index equal to tickers. This is creating a pandas series from our optimized weight vector and using the tickers list as the index. We'll need these for further calculations. Next, we're going to take the top 10 securities by weight. We use the sort values method with ascending set to false to sort in descending order, then select the top 10 rows with head 10. We also make a copy of the series just in case we need it later. Now, let's clip any tiny negative numerical artifacts that might be present in our weights. This is done with the clip method, setting the lower bound to 0. Next up, we renormalize the top 10 weights so they sum up to 1. We do this by dividing the series by its own sum. Finally, we're going to create a new full weight vector where all other securities have a weight of 0, and only the top 10 have their corresponding weights from top 10. This is done with a pandas series filled with zeros, then setting specific values based on the index. Now that we've set up our rolling window, let's take it to the next level by implementing a multi-period backtest with rolling rebalancing. This is where things get really interesting, as we'll be simulating multiple periods of trading, adjusting our portfolio weights accordingly after each rebalance date. We're going to choose between monthly or quarterly rebalance dates, depending on our strategy's requirements. For each rebalance period, we'll use the past year's returns to estimate our mean and standard deviation. This is crucial for accurately modeling market volatility and risk. Next, we'll call our optimized portfolio function using the previous weights as input while accounting for transaction costs that can eat into our profits. These costs are calculated based on a specified rate, turnover ratio, and current portfolio value. Now that we've cleaned and formatted our weights data in the previous cell, let's create a simple bar chart to visualize these portfolio weights. We start by importing Plotly Express, which is a high-level interface for creating various types of visualizations. This import allows us to quickly create interactive plots without needing to write as much code. Next, we sort and select the top 10 weights in descending order using the sort values method and head function from our clean data. We then use Plotly Express to create a bar chart. We specify that we want to plot the values of the sorted weights on the y-axis, while using their corresponding tickers as labels on the x-axis. The title of the chart is set to portfolio weights, and we add labels for the x and y-axis. We also configure some additional settings, such as removing the legend, rotating the x-axis tick labels by 45 degrees, and specifying a larger width and height for the plot. Finally, we display the chart using the show method. Now we're setting up the data and basic objects for our analysis. This is where things get interesting. We've already loaded in some libraries, including NumPy and Pandas, which are essential for any data science project. We're working with a data set of adjusted close prices, which are essentially the closing prices of stocks after accounting for dividends and splits. These prices come from Finance, so make sure you have that library installed and imported. We'll be using this data to calculate returns and perform further analysis. Now, let's take a look at what we're doing with the prices data frame. We're dropping any rows with missing values, which is essential for our analysis. This ensures that we only work with complete and consistent data. Next, we're calculating the returns by taking the percentage change of the closing prices over time. Again, we're dropping any rows with missing values to keep our data clean. We've also defined a few key variables: tickers, which is an array of stock symbols, and N, which represents the number of stocks in our dataset. Finally, we're defining an annualization factor, which accounts for the fact that there are approximately 252 trading days in a year. This will be important later on when we calculate annualized returns. So here we have a cell that calculates the month-end rebalance dates for our returns data. This is important because we want to identify the specific dates when our portfolio is actually rebalanced, rather than just any arbitrary date. Let's quickly go over the imports, which are Pandas and NumPy. These are essential libraries for data manipulation and analysis in Python. Now, we define a function to get month-end rebalance dates. It resamples the returns data by month, taking only the last day of each month. This gives us an array of month-end dates. We then filter out any non-trading days from this list, using a lookback period of 252 trading days. This means that if a date is not in our index or does not have enough trading history, we'll skip it. Finally, we sort the valid rebalance states and return the first 10 values for good measure. The output will show us how many valid rebalance states there are and what they are. Now we're defining the initial portfolio value and weights in this cell. The initial portfolio value is set to $1 million, which represents the starting amount of money that we'll be working with. The previous weight vector wprev is being initialized differently here than it was before. Instead of editor, this means that at the start, we're fully invested across all N assets. We also define 3 key parameters: gamma, cost rate, and turnover limit. These values will be used later on to determine trading decisions. Let's walk through this Jupyter notebook and see what's happening. We're starting with a function called optimize portfolio. This function is used to optimize the portfolio by finding the optimal weights of securities given their expected returns and covariances. The function takes several parameters, including the expected returns and covariances of the securities, as well as some additional parameters that control the optimization process. The main goal of this function is to maximize the return on investment while minimizing transaction costs. It uses a quadratic programming solver to optimize the portfolio weights. Let's take a look at how it's used in the code. We're calling optimize portfolio within a loop, where we're iterating over a list of rebalance dates. At each iteration, we're estimating the expected returns and covariances of the securities using historical data. After optimizing the portfolio, we're checking if the optimization was successful. If it wasn't, we're setting the weights to the previous values and skipping the transaction costs for that period. Now, let's move on to the main part of the code, which is the backtest loop. Here, we're iterating over the rebalance dates again, but this time we're using the optimized portfolio weights to calculate the returns and growth of the portfolio. We're also keeping track of various metrics, such as turnover and transaction costs, which are used to evaluate the performance of the portfolio. Finally, at the end of the loop, we're displaying a data frame that summarizes the results of the backtest. This data frame shows the portfolio value after each rebalance period, along with other relevant metrics. Overall, this code is implementing a mean variance optimization algorithm to optimize a portfolio and then using it to run a backtest on historical data. The goal is to evaluate the performance of the optimized portfolio over time and understand how well it would have performed in practice. Now we're going to visualize our backtest equity curve using Plotly, which will give us a better understanding of how our portfolio performed over time. We'll plot this in an interactive chart that allows us to hover over specific points for more information. Let's take a look at the imports first. We've got Plotly Express imported as PX. Now, let's get to the code where we create our line plot using PX line. We're passing in our backtest data BT, specifying the x-axis as the index and y-axis as portfolio value. We also add some labels for clarity, including a title that mentions rolling optimization with costs. We update the layout by adding a tick prefix of dollar to the y-axis, so all values are properly formatted as dollars. Finally, we display the chart using Figma@Show. This interactive visualization will be super helpful in understanding our backtest results and making informed investment decisions. Now that we've calculated the returns for our strategy, let's calculate the S&P 500 returns over the same period. This is important because it allows us to compare our strategy's performance against a widely recognized benchmark. We're importing the IFinance library, which will be used to download historical prices for the S&P 500 index. Next, we drop any missing values from this calculation. Now, let's loop through our valid rebalance dates and calculate the S&P 500 value at each date. This involves calculating the cumulative growth of the S&P 500 returns between each rebalance date. We're using NumPy's prod function to calculate the cumulative growth, which is the product of 1 plus each return in the period. Finally, we create a pandas data frame with the S&P 500 values at each rebalance state and merge it with our backtest results. Now, let's create a line graph that compares the value of our optimized portfolio to the S&P 500. We're doing this by superimposing the S&P returns on top of our existing graph. We'll import the necessary library from Plotly Express, which is a high-level interface for creating various types of plots. This cell matters because it allows us to visualize how our optimized portfolio is performing relative to the market as a whole. By comparing these two values side by side, we can get a better understanding of whether our optimization strategy is successful. Now, let's create the graph using the Plotly Express library. We'll pass in the data and specify what elements we want to include on the graph. We'll display the title of the graph as Optimized Portfolio vs S&P 500 and customize some of the layout settings to improve readability. Finally, we'll update the y-axis label with a $sign prefix so that our values are displayed in the correct units. With these changes, we can now visualize how our optimized portfolio is performing against one of the most widely followed market indices out there. Now that we have the comparison of our portfolio and SPY, let's calculate some key metrics. This cell does two main things. It calculates monthly returns from the equity curves and then uses those to compute annualized statistics. First, we're importing some necessary libraries for calculations. As you can see, there are a few import statements here. Next, we'll be calculating the monthly returns implied by our portfolio and SPY value columns. This is done using the PCT change function from Pandas. We're storing these returns in new columns called portret and spyret. Now that we have those returns, let's drop the first NaN value since it's not representative of actual performance. The resulting data frame is assigned to the variable rets. Next, we'll calculate some important statistics: annualized returns, annualized volatility, and Sharpe ratio. We're doing this because monthly data isn't always as useful as annualized metrics. By multiplying the monthly return by 1 plus 12/length of data, we get an approximation of annual return. Now that we have all these values, let's print them out so we can easily see how our portfolio is performing in comparison to SPY. In this cell, we're adding the whole Dow equal weight portfolio as a benchmark to compare our optimized portfolio against. This is an important step because it gives us a baseline to measure our performance against. First, we import the necessary libraries, NumPy and Pandas. These are standard imports in Python for numerical computations and data manipulation. Next, we calculate the weights for an equally weighted Dow portfolio. We do this by creating an array with each stock having the same weight, which is 1 divided by the number of stocks. Then, we loop through each rebalanced state and calculate the returns for the equal weight Dow portfolio over each period. We use matrix multiplication to calculate the daily returns of the portfolio. We also track the gross growth of the portfolio over time, which is simply the cumulative product of 1 plus the daily returns. Finally, we combine this benchmark with our optimized portfolio backtest and display the results for comparison. Now this will give us a visual comparison of their performance over time. Let's take a quick look at these imports. We've got Plotly Express being imported as PX. Nothing too exciting here, just setting up our plotting library. Now, let's move on to the code where we create this plot. We're using the reset index method from the BT-compare data frame to get it into a format that Plotly can work with. Then we define what we want to plot: the rebalance state on the x-axis and 2 y values, one for the portfolio value and another for the equal weight Dow 30. We also set some labels and specify the width and height of our chart. Finally, we use update layout to customize some more settings, like adding a $sign prefix to the y-axis and changing the hover mode. This will give us a visual comparison of how these two portfolios have performed over time. Now we're going to calculate some important metrics from our backtesting results. First, let's import the necessary libraries, which is just Pandas for now. We'll create a copy of BT-compare and store it in BT metrics. This variable will hold our backtested portfolio values over time. Next, we're going to adjust the starting date of our metrics to be 1 day before the first rebalance. This might seem minor, but it's actually really important for calculating returns accurately. We'll then set the initial portfolio value and Dow Jones equal value both to $1 million. Again, this is crucial for getting the correct return calculations. After that, we'll sort our metrics by date to ensure everything is in order. Now we're going to calculate some key statistics from these metrics. We'll start by finding the monthly returns implied by our portfolio values and Dow Jones equal value over time. This will give us a clear idea of how our portfolio has performed relative to the market. We'll store these monthly returns in new columns called OptRet and DowRet. Next, we'll drop the first NaN missing value from our returns data. This is because the first month's return can't be calculated accurately, so it's best to exclude it for now. Finally, let's calculate some annualized statistics from these monthly returns. We'll use the formula for geometric mean to find the annualized return, which gives us a better idea of long-term performance. We'll also calculate the annualized volatility and Sharpe ratio using standard formulas. This will help us evaluate how our portfolio has performed relative to other investments. These metrics are super important because they give us an accurate picture of our strategy's potential returns and risks over time. Now that we've compared the performance of our optimized portfolio to a simple equal-weighted Dow Jones index, let's calculate the respective compound annual growth rates. This cell will give us an idea of how each investment strategy has grown over time. We'll start by importing the necessary libraries in this case. Just some basic ones like NumPy and Pandas aren't needed here, so we can skip that part. We're setting initial val to $1 million for our calculations. We also grab the final portfolio value from our optimized strategy and the Dow Jones equal-weighted portfolio. Next, we calculate the number of years each investment was held for by dividing the length of our returns array by the number of years in a year. This will help us with our CAGR calculation. Now, let's calculate the compound annual growth rate for both portfolios using the formula final values slash initial value 1 slash number of years 1. Finally, we print out the results to see how each investment strategy has performed over time. This will give us a clear picture of which approach has delivered better returns. In the final cell of our notebook, we're simply ending our execution here. This is the last instruction for the kernel to run, marking the end of our Jupyter workflow.